Let's talk about specific impulse. Specific impulse is one of many performance parameters of propulsion systems. It relates the force output of an engine, known as its thrust, to its propellant consumption. Usually it's defined with respect to propellant weight, but can also be defined with respect to propellant mass or volume. In this video, I will talk about weight-specific impulse. In the context of spacecraft propulsion, impulse is the integral of the thrust produced by an engine over the time interval during which the engine is active, also known as its burning time. Thrust can be defined as the mass flow rate times the exhaust velocity with respect to the moving spacecraft. Specific impulse is the ratio of the impulse of an engine to the weight of its propellant. Formally writing down these definitions, we get the equations pictured on the left column. From here, we can approximate the mass flow rate and the exhaust velocity as being independent of time or constant. This simplifies our integral expression into the second line on the right. For our applications, the mass of the spacecraft is constant and only the mass of the propellant changes with time. This means that the rate of change of the propellant mass, m dot, is equal to the mass of the propellant divided by the burning time. Plugging the expression on the third line into the one on the second line, we reach a simplified expression for specific impulse, which is exhaust velocity divided by gravity. Why is specific impulse in units of seconds? From dimensional analysis, we see that dividing velocity by acceleration yields a resulting dimension of time. The reason why we divide exhaust velocity by gravity is historical. In order to arrive at a value with neutral units, space programs using metric units and those using imperial units could divide their exhaust velocity by either 9.8 meters per second squared or 32.2 feet per second squared. Now we have an expression for specific impulse, exhaust velocity over gravity. But what value of gravity is used? In Newtonian mechanics, we know that the gravitational force between two bodies is inversely proportional to the square of the distance between them. This means that ISP, as a function of gravitational acceleration g, would vary based on the spacecraft height above the Earth. In order to compare performance of different engines, we want expressions independent of height. As a convention, the gravitational acceleration used in the calculation of specific impulse is that seen on the surface of the Earth, roughly 9.807 meters per second squared. If ISP tells us about the efficiency of an engine, do we always want to use an engine with the highest ISP? Why would a mission leverage an engine with lower ISP? Rearranging the definition of ISP that we derived previously, we reach an expression in terms of thrust, mass flow rate, and the gravity on Earth's surface. To maximize ISP, we can maximize thrust or minimize mass flow rate. Ideally, we would do both. In reality, we have to prioritize how we want an engine to perform based on the mission parameters. Here are some ranges of required power versus ISP for different kinds of propulsion technologies, and what they're used for based on their performance parameters. Note that this graph expresses power versus ISP instead of thrust versus ISP. However, the relationship between power and thrust is displayed in the expressions to the left of the graph. Finally, here are concrete examples of propulsion technologies and their performance. While Hall thrusters have 3 times better ISP than the Space Shuttle main engine, they can only produce 10 to negative 7 times the amount of thrust. Only one of these can launch humans into space, but the other might be much more economical for maneuvering an uncrewed satellite. Thank you for watching this video.